Hi, my name is Madison Rye with Ally PLM. We're here today to talk about Solid Edge ST3 simulation. I want to show you how, with Solid Edge simulation and ST3, we can further reduce the need for physical prototypes through a wider range of simulation tools. That's what I'm here today to show you with this Dixie chopper assembly. It's a lawnmower, spindle with a blade attached by a mounting bolt, and this plate represents the deck of the mower. The first thing I need to do in any simulation is figure out what physical situation I'm trying to simulate. In this case, what I'd like to do is see what happens when the blade hits the rock, see what happens to this shaft in displacement and stress. The other thing I'd like to do is determine if my natural frequency of this system is in my operating range of the engine of the lawnmower. And we'll talk more about that in a little bit. With simulation, you can very easily follow your ribbon bar through pre-processing or preparing your model for solving, and then post-processing or reviewing the results. Now what I want to do first is simplify my model because of the fact that these little edges and the little grooves are going to cause my mesh size to be extremely small. So I don't want to have those in my simulation because they're going to have no bearing on my study that with stress and displacement here. So I can just go into the part, and I'll turn off my background assembly since I don't need it, and I will simplify by just deleting the faces that I don't want, such as these grooves there. And similarly, I can window select and delete the rounds that I don't want. That will cause my element size to be too small. Now I can get a nice mesh on this part without having tiny elements to drive my solve time up. If I go back to my assembly, I just need to tell it that I want to use that simplified part. So now I'm going to start with my ribbon bar and create a new study. I have the choice of linear static, modal, or buckling. Linear static is where I get my stresses and my displacement, so that's what I'll select first. I have the choice of tetrahedral, solid elements, or surface elements. These solid elements here are for parts like this that are solid, and they're those little triangles that you see all over the part when you have the mesh. Surface elements are for parts that are very thin compared to their length and their width. I'm going to choose this solid element, and I'll explain why in a little bit that I didn't choose the surface element for this particular part. That takes me right to my next step, which is defining the geometry. I can do that quickly with a fence select, which takes me to my next step, which is loading. I have all the standard loads here. New with ST3, we have torque and bearing load. We also have displacement, temperature, gravity, centrifugal, and pressure. In this case, I'm going to choose a force that simulates this thing hitting a rock. Now with this synchronous technology, I can very easily change my force to the direction that I want it. There I have my loading, and I move on to constraints. And all this means is how is this part held down, because it's obviously not floating out in free space. So I'm going to constrain the part where it's attached to the frame of the mower. Now what that means is all these surfaces around the outside, well first of all, I talked to you about those surface elements. They're all tetrahedral little triangles all over the place. Where those triangles meet, we call those nodes, and the simulation determines when you load a part how those nodes move in X, Y, and Z. So you have 3 degrees of freedom for a solid element. It's motion in the X, Y, and Z. We call those translational degrees of freedom. What I'm saying here by constraining this is all the nodes that lie on the outside surface of this plate cannot move in X, Y, or Z. New with ST3, we have a user-defined constraint that allows us to select which constraints we want to say are equal to 0. Like if I wanted X to be 0 and Y and Z I wanted motion in, I can do that with this new user-defined. That moves me right on to my connectors. I need to tell simulation how these parts are connected. My auto connection is extremely easy to use. I have glued or no penetration. What glued means is those elements that lie in contact on these two surfaces, for example, cannot move or actually have to move together. So their motion in the X, motion in the Y, and motion in the Z is equal. They are literally glued together. They can move, but they have to stay. The nodes have to stay together. No penetration means this part could slide relative to the other, or it could come off the other part, come apart. It just can't go down through the part. It can't penetrate into the part. I always start with glued connection. If you need to make it more complicated later, you can do that. The search distance here, I talked about the surface elements. They're represented by a 2D geometry that's usually placed at a mid-surface, in between the top and bottom surfaces of the plate. So those elements might not actually be in contact with this spindle, so I might have to increase the search distance to account for that. Or if I'm using no penetration, I could increase the search distance if there's a gap between my parts. Once I select that, I get very nice feedback on what my connections are, and those are the ones that I want. So I create my connectors, and I can move on to my bolted connection. This is new, and it's fabulous because I can select one bolt, and I get all my bolts on the bolt hole circle. What this means is you'll notice that I don't actually have the bolts in there, and the reason for that is I'd have to have a tiny mesh on those bolts, which would drive up my solve time. And I very easily, simulation can represent a bolt with the beam element through the center of where the bolt would be. The node at the top of the beam element is connected to all the nodes on the circle. The node at the bottom is similarly connected to all the nodes on the bottom circle. And it looks like a spider web when it's done, which is why it's called a spider connection. Now you notice too that I did not put a glued connection between the plate and the spindle. I can take care of that here. And I can also put my bolt all in one container so that my tree is cleaned up. If you've ever tried to do a pre-stress force without by yourself, it's extremely hard to do actually to simulate. And here, simulation handles that very nicely for you with just an enter of what that pre-stress value is. And you'll see here in the tree, I have one connection for my bolted, all my bolted joints, which is very nice because it cleans up my tree. Also, we have this new edge connection, which if you're using surface elements, you're going to want to use that if you have two plates that are perpendicular to each other, because you'll get an edge condition, and now we can handle that connection with our new connector. That brings me to my meshing, and I'm just going to take the default mesh. Simulation does a very nice job of giving me that default. You'll notice when this comes back that I'm only going to have one element through my thickness. My solid elements that I talked to you about have 3 degrees of freedom: motion in the X, motion in the Y, motion in the Z, translational degrees of freedom. They don't have any rotational degrees of freedom. So to capture the bending of this plate, I'm going to need 2 or 3 elements through the thickness here. Now when this comes back, you're going to see that I'm just going to have one. That's why our rule of thumb is always have 2 or 3 elements through the thickness here. But because I happen to know with this situation that this plate doesn't contribute very much to bending. The plate doesn't bend very much, which doesn't contribute anything to my stress and my displacement here. That's significant. I've run it with 3 elements, 2 elements through the thickness, and there's no significant change in my results. So I can just use this one element, which is why I did not use those surface elements. I'm going to click Solve here, and while this is solving, now most situations you're going to want to capture the bending through your parts. So you're going to use the solid or the surface element. The reason for that is because if you imagine I'm going to put 2 or 3 elements through here, they're going to have to be very tiny, and they're going to cause all these other elements to be very tiny, which is going to drive up my solve time. A surface element is, like I said, represented by 2D geometry at the midplane here. It actually has translational and rotational degrees of freedom. So it has the motion in the X, Y, and Z, but it also has rotation about the X, rotation about the Y, and rotation about the Z. So if I'm using plates or things that are very thin compared to their length and width, I'm going to want to use those surface elements because I can use I just need one through the thickness because it captures the rotation, and also I can use a bigger element because it's represented by that 2D geometry, and I don't have to have all those tiny elements through the thickness there. My results are back, and you'll see that this is von Mises stress, and if you remember, von Mises determined that even if you're calculating your principal stresses in the X, Y, and Z direction, if those stresses are all less than the yield stress, the combination of those might still fail your part. So he developed an equivalent stress, and that's what we use. We call von Mises stress, and we compare it to our yield stress to see if our part will fail. I can use my probe tool and select here, and I can see that I've got about 120 megapascals. Now I can take all this to Excel if I wanted to, copy and paste. Very nice. This part is aluminum 1060 aluminum, so the yield is about 27.5 megapascals, so I'm over my yield here, which is an issue. So I need to think about, what am I going to do? Am I going to change my geometry here, or am I going to change my material of my part? But before I do that, what I want to do is take a look at my natural frequencies. So I'm going to create a new study, and this is going to be a modal analysis. And here I'm just going to take the first 4 modes, or the first 4 frequencies the thing is going to vibrate at, and I'm going to, with a frequency range, it usually comes back with a fine frequency range there. Usually the rule of thumb is like 3 or 4 times what your operating frequency is to capture all the modes in it. And I could, if I was looking for more, I could, increase this number, but this is usually pretty sufficient. It usually gives you very good default. That takes me to my defined geometry, and I can then select again on that. And I think let me just check here that I got everything, because I think I clicked too fast there. Yep, I have everything. I can always go to the tree here and just make sure that I have all my parts. Now you'll notice here in my loading, I can't specify a load. It's all grayed out. The reason for that is because a modal analysis uses a unit force to excite this, just like you're pinging you're pinging a tuning fork or something. So you don't need to specify an input force there. Next thing I need to do is just tell it how it's tied down to the frame of the mower. And again, I'm making those elements here on the surfaces, their degrees of freedom are all constrained. Then I can go to my auto connection again and show you how easy this is. Just check real fast to make sure I've got all 3 of my connections, that I didn't misclick or anything. And I do. Then I can use my bolted connection. And I'll input my pre-stress value, make my connection, and put those all in one container. And that moves me right along to meshing and solving. And I can just click Mesh and Solve here because of the fact that I know my mesh is good. I reviewed it already. So what I wanted to talk to you about here is there are 2 types of vibration, free vibration and fixed vibration. Or, I'm sorry, forced vibration and free vibration. Like I said, when you ping a tuning fork, that's free vibration. It's just vibrating at its natural frequency or its resonance. And all that means, it's dependent on mass and stiffness of the part, and all it means is that at that point, the amplitude of my displacement is going to be very high. So I want to avoid operating in that range. Now forced displacement is when I have an input vibration to the system. And let's say I get a ding in this from where I hit the rock or whatever, or I have a grass buildup here, or it just was assembled a little bit off center. Anytime my center of mass is not at my center of rotation, I'm going to have a forced vibration input. And it's going to be at the frequency that this thing is rotating. And for this Fixie chopper mower, it actually operates at about 3,600 RPM. So if I divide by 60 there, I get 60 hertz. 60 hertz is going to be my input or my operating frequency of this mower. Now, what I don't want to have happen is my natural frequency or any of my frequencies this thing's vibrating at to fall into that range, anywhere around there. My rule of thumb is that I want my first mode or my first natural frequency to be twice my operating frequency. So I'm at 60, I want my first one to be at least above 120. If you've never thought of vibration before, you can go to YouTube and take a look at the Tacoma Narrows Bridge, and you're going to see it's absolutely amazing that this bridge goes in a wave because of the fact it was built in 1940, and several months after it was built, it actually collapsed because of the fact that the wind happened to be at the right speed. It wasn't that high, it was 40 miles per hour, to excite a natural frequency of the bridge. And this concrete structure, it literally looks like it's a wave going down it. So take a look at that when you have a chance. If you haven't thought of vibration in the past, you want to think about that. So now I have my results here, and I can go up and take a look at my first mode, and I can see that it's about 86 hertz. Now 86 hertz is not double my 60 hertz, so I've got a problem with my vibration as well. So I don't want to I don't want to excite that natural frequency because of the fact that this thing is going to be at its maximum displacement. I don't want to have that condition. Now, and if I wanted to see what that mode shape looked like, this is exaggerated, of course, but that's what it looks like. It's going to move much more than it normally would because of this forced vibration input. So I need to decide now, what am I going to do? Am I going to go back to, I'm going to go click here to go back to my static study. Am I going to change the material, or am I going to beef this part up? Well, I think I can accomplish stiffening this up so that I can increase my natural frequency and also reduce my stress at the same time. So let me show you how easy that is to do in simulation. I can just go back right into my part here, and I can use the live section to make this change, which is very handy. Let's see. Here's my live section. I just pick a plane, and then I can use my driving dimensions to make my changes. And similarly here, I can drag this down if I want to, or I can type in an exact number. And you'll notice that my live rules are at the bottom, and that is keeping my design intent in place. And we're actually going to have a lunch bite session on these live rules, so look for that because it'll help explain how to use those to their maximum. I could go back here. Now this is the best part about the integration. I'm just going to hit solve here because this is the best part about the integration between these two things. Solid Edge and simulation are so tightly integrated that I don't need to go back out and make my changes, because that's what I'd have to do before, then bring them back in, simplify my part again, and then redo my analysis. That takes a lot of time actually, and this integration makes it just the click of a button. All I have to do is solve this again because my geometry is updated automatically. Now that brings me to talking about the solver a little bit. We use the Nastran solver, and it is literally developed by rocket scientists. It came from NASA, and they used it on the space shuttle. It was developed for that. So it is the industry standard, and actually a lot of the car companies now are going to the Nastran solver because of the fact that it's been proven to be more accurate. So you know when you're getting results here with Solid Edge simulation that are extremely accurate in your analysis when you set everything up correctly. You're getting very good results here. The other thing, real quickly, I wanted to mention that is new with Solid Edge Synchronous Technology Simulation 3 is ST3, is that if, let's say that your area of concern is a hole or a bolt hole like this, we now have offset surface, so I can put an offset surface around this ring, around this bolt hole if I wanted to, and put a finer mesh inside and a coarser mesh outside. Now I can't have a tiny mesh inside and a huge mesh outside. You have to step it out. But that'll at least allow you to not have that tiny mesh everywhere and drive up your solve time. And now we have our results, and you can see that we're about 6 megapascals. So that's taking care of our stress problem. Now what I can do is go back, and all I have to do is go here to the tree, and you'll see that I get some extremely nice feedback. Actually, before that, let me show you a couple things here with the viewer in my post-processor or my results viewer. It's hard to see the deformation here. What I like to use this this percentage increase so that I can see it better. It just magnifies everything, exaggerates it so that I can see it. Then I can animate it, and this gives me an extremely good idea of how my part is deforming when it is loaded. Very critical in engineering. The other thing, and this just I love, but you know, I think people get spoiled by their clicks of a button. I used to spend a lot of time when I worked at Cummins putting together test cell data that matched up with theoretical data, and the reporting, it took a long time to do. Now, new with ST3, we can put this in a Word document, but this is fabulous to me. That at a click of a button, I mean, I would spend probably 4 or 5 hours putting together reports for each test cell run. Here, I get something that's way better than I would have ever created, and I get the screenshots and all the results here at my fingertips with just a click of a button. Very nice, very convenient, and you can add your company logo in here. So the other couple things here with the color bar, if you want to change the way things look, you can. There's a display that you can change. Also with the mesh, if let's say I want to take a look at, displacement. Oops, I got to go back to my home page. Say I want to look at displacement. And again, I'm going to amplify that so I can see what's going on, how this part is deforming when I'm loading it. Let's say I want to look at the bottom of the part and I can't see it. I can go to my mesh here and just delete, or not delete, unclick those parts so that I can see the bottom of things, determine what's happening. Now, just like in Solid Edge, you can use clipping planes to see what's happening on the inside of your model as well. So I can go and set my plane here, and I'm going to choose a reference plane. So I can see now with my clipping plane exactly what's happening on the inside of my model as well. The other thing I wanted to mention is that here in the geometry tree of simulation is the material, but also if I'm using those surface elements prior to ST3, I could only do one thickness for all the surface elements in a model. Now for each part you can specify a thickness in here in the tree, which is very handy. So all I have to do now when I want to go back and take a look, I'm going to close out of my results here, I'm going to go back and take a look at what my modal analysis is. The same thing, I just go to my modal study and notice I get really nice feedback here with the exclamation points that my mesh is out of date because I've changed my geometry. All I'd have to do here is click Unmesh or Solve and Mesh and Solve. But to save time, I'm going to actually just open up my other results so that I can not have to spend time here doing the solve, so that you can see what my natural frequency ended up. And you'll see now, these are the results with my increased stiffness, is that it took my first natural frequency, my first mode, up to 127 hertz, which is double my 60 hertz operating range. So I've now solved the problem with stress, and I've also solved at the same time the problem with my natural frequency. That's all I wanted to show you here with simulation today. I hope that you've learned quite a bit from this, and that you realize that we now can better model more real-world situations with the increased variety of tools that we have inside of simulation. The last thing I wanted to do is show you what options that we have. Solid Edge simulation, floating license, I have the prices listed here, that you can add on a floating license of simulation to your existing Solid Edge seats. Here is Solid Edge Premium Upgrade, so let's say you have a seat of Solid Edge and you want to upgrade it to include wire harness, express route, and simulation. This is the upgrade price. And then if you just want to purchase outright a Solid Edge Premium seat that includes Classic, Solid Edge Classic, wire harness, express route, and simulation, the prices are here. Please contact Kim Corbridge. He's our sales manager, and here is his contact information. Thank you again for your time today. If you have any questions, you can either email Kim or myself, Madison Rye. Thanks very much.